Okay, morning.
Good morning.
Okay, screen's nice and smooth today.
Looking pretty smooth today.
Really? Huh. I have satisfied the internet gods for about the past 3 weeks now. This is amazing. Anyways, so we were discussing the multi-phase flow equations in a very general framework. These are, you can find these full equations derived in a lot of multi-phase flow books. They assume nothing. It really assumes nothing as to the material or its distribution inside of the computational or inside of the infinitesimal control volume, just that there are volume fraction gradients, things like this. And now the interpretation as to whether it is a sharp interface between gas and liquid, like a droplet, if you're resolving the droplet, or if it's a bunch of particles, is dependent on what you are modeling and the particulars and the particular submodels that you choose for your equations. And those get to be extremely domain specific. So I can't possibly go over all of those. You could spend an entire course just on these multi-phase flow equations and then how to apply them for different situations and just discussing their properties. And yeah, and then I know Bala teaches a course in multi-phase flow, but I don't know if he gets into these super general ones. I don't know. But anyways, so the equations I showed are very general, and they are the basis for these volume of fluid methods. The methods related to the volume of fluid method, meaning you solve the volume of fluid equations, but you don't use their special algorithms. They serve as the basis for the Bernoulli-Nunziato equations, and I will discuss what those are because they're used a lot in high explosives modeling. They're grossly overused in particulate flows, so if you work in multi-phase flow and combustion, you will encounter them at some point, and then Eulerian particle methods. And so basically these equations work for either or. It just depends on this on basically the exact sort of models that you use and modeling choices that you basically make. Now, one thing is that these equations are very general, but they're also incomplete. So if you count up the number of unknowns, you have the volume fraction of phase K, you have the density of phase K, you have the velocity of phase K, and you have the total energy for phase K. And so if you basically count them up, and just assuming we're in a 3D flow, you have 6 variables per phase that you don't you have 6 variables per phase, but if you count up the number of equations that we have to work with, we have continuity for each phase, we have momentum, so 3 of those, and we have energy. And if you count them up, we have 5 equations to work with per phase. So I think you can see here there is a bit of an issue here, is that there are more unknowns that come from the volume fraction than there are equations in which to solve them. And you may be thinking, okay, well, it's not that bad. You can apply the condition that the sum of the volume fractions for all the phases has to be 1. So, so basically what this means is that we can reduce our number of unknowns by 1. 6n phase minus 1 would be the total number of variables. Would be 6 times the number of phases minus 1, and this minus 1 comes from the fact that that we don't need to compute all the volume fractions. Is that we can use this definition here to find the very last one. Okay, but at any rate, even if there are only 2 phases, we still have 1 extra unknown, and that is a volume fraction. And so there's a compatibility condition here that needs to be made. And then so you need to make assumptions. And the key assumption with with these multi-phase flow methods is what you do with the volume fraction equation and then also some other things. Okay, and so and so I'm just going to go over various forms of this or of these multi-phase flow equations. And really what is typically done for the volume fraction equation is that they either solve d alpha k dt equals some sort of phase change source term. I'll just call this alpha dot k for the time being. Or they solve partial alpha k partial t plus the divergence of alpha k vk, and that is equal to some change of volume due to chemical reactions. Okay, and so typically it is either this or this that is used, and this looks like a very subtle distinction between the two, but they have massive implications into the nature of your flow. And so this looks very subtle. And in fact, it's only by working with these multi-phase flow equations for say very rigid particles, where you solve it in this form, that I really started to understand the difference between this operator and this operator here. Okay, and so really for the multi-phase flow is they tend to augment the governing equations with a volume fraction equation is basically what they do. Okay, and so now we'll just go over various forms of the multi-phase flow equations, and then so we're going to take our general equations and we're going to basically simplify them down into something called a 5-equation model. Now, you will see this used a lot by mathematicians and some folks. There's a 5-equation model, a 4-equation model, a 6-equation model, blah, blah, blah. And it keeps going and going and going. And there's a 7-equation model, etc. And so basically, the sort of number here is basically what you would get if you counted up the number of partial differential equations that you need to solve for a non-reacting one-dimensional flow. Okay, and so that's basically how they define the 5-equation models, that in 1D without chemical reactions, you have to solve 5 partial differential equations. For a 7-equation model, you need to solve 7 of them. Okay, so anyways, so we're going to derive the very common 5-equation model. It's starting to be used a lot these days. My group uses it for various applications. So here we apply an assumption called homogeneous flow. And what homogeneous flow means is that the velocity of all the phases is the same. So you could say that Vk is just equal to the velocity for all k. So that is, if you have a gas liquid flow, they are equal to the same velocity. And that allows us to make an assumption, or to make a simplification. We're going to assume mechanical equilibrium, and that is that the pressure of the gas and the liquid or the solids is the same. And so, go away. And so basically that means we only have one pressure. We don't have a pressure for the gas and a pressure for the liquid. And we're also going to assume thermal equilibrium, and that is the temperature of all the different materials are the same. In basically in each computational cell. And some folks will relax this assumption here to where they will assume different temperatures. And if they do that, you have to have 2 energy equations, one for the gas, one for the liquid, so that you can track both temperatures, and then you wind up with a 6-equation model. Okay, and so now, and so these are the base assumptions that we're going to apply to simplify that massive mess of the governing equations that I scribbled above. So first, we will assume that the liquid volume fraction is a passive scalar. And so that means we solve d alpha k dt is equal is equal to basically alpha dot, which is just the change of volume due to phase change. Okay, so you could just say that that is the mass exchange divided by the volume of phase K. And of course, this needs to define carefully so that it's sort of consistent. And so this here is a scalar advection equation, and this basically means is that the sort of that if I'm following a bubble where say alpha is 1 inside and alpha is 0 outside, all this equation does is it just moves the bubble around with it just moves the bubble around like with the fluid flow. That is it. So that is all this does. Okay, and so that's sort of our ansatz here, is that we are assuming this form of the equation for the motion of the volume fraction. No, and then computationally, if your flows are compressible, typically you will approximate this term. You will not solve this term directly. Instead, you will say that this term is equal to the divergence of alpha k times v minus alpha k times the divergence of the flow velocity. And there are various compressible flow numerical algorithm reasons for doing that. I'm not going to get into those, but just be aware is that sometimes you will see this term written like this. And mathematically, they are identical, but there are numerical advantages to solving them like this, just because you can do it in a more conservative way that basically matches how compressible flows are solved. But again, that's a whole different class getting into the reasons why you do that. Okay, so are there any questions? Okay. Now, what the homogeneous flow assumption allows us to do is it allows us to solve a single mixture momentum and a single mixture energy equation. Is that basically we can combine momentum and we combine all of the momentum equations for all of the phases into one, and we can combine all of the energy equations into one, because we are assuming that the velocity is common between all of the phases, and we are assuming that the pressure is common between all of the phases, and we are assuming that the temperature is common between all of the phases. And so basically that allows us to greatly simplify the governing equations. And so basically we look at the governing equation, or so here's conservation of momentum for phase K. And basically, we are just going to, for demonstration purposes, I'm just going to assume gas and liquid, so two phases, and then we just add them up. But now what we can do for our assumptions here is that I can assume that PK is PG, or that PK is P, because again, the PG is equal, basically because the pressure for all the phases is the same. And I can assume that the velocity for all the phases is also the same. So I can replace VK, which is just the sort of velocity of, say, if it's a droplet flow, it's just the velocity of the droplets. I can replace that with the velocity of the mixture, or just V. And so doing that, and then doing that for both equations for the gas and the liquid, and summing them up, you can derive what's called a mixture momentum equation. Okay. And so under these assumptions here, we can basically just strip off the subscript k's, which is all I did. I just copied and pasted this and deleted them. Okay, and so far this doesn't look like this helped very much. But now let's add up the momentum equation for gas and the liquid. Okay, so I'm just going to assume 2, but this extends arbitrarily to if you have 10 different phases, this also works. You just need to be a bit more careful with your sums. Okay, so I'm going to take the conservation of momentum equation for the gas and the liquid, and I'm going to add them up. And so that's what I've done here, is I got the gas phase sort of time derivative, time rate change of momentum here, and I have the liquid time rate change of momentum there. So I've literally just taken this equation for gas and this equation for liquid, and I just added them up. Okay, and so then you wind up with these terms here. And so you have the divergence of alpha s, or of alpha g rho g times v squared, plus the divergence of alpha l rho l times v times v squared plus, actually this should be not divergence, that should be gradient. And we have the gradient of alpha g times p plus the gradient of alpha l times p. And then we have all these interfacial terms to sum up. So we have, and the interfacial pressure will be the same. So we have just the interfacial pressure times the gradient of alpha or the volume fraction of the gas plus the gradient of the volume fraction of the liquid plus the viscous terms for each phase plus an interfacial shear stress term and plus a phase change, a momentum exchange due to phase change. Okay, and then also if say you wanted to have, say you said you had a sort of droplet flow, you could have a drag force here, but for one of the phases, the drag forces would be positive, and for the other momentum equation, they would be negative, and so they would exactly cancel out. But now this looks like I took a complicated equation and I made it even more complicated by adding a second equation to that. But this equation actually simplifies extremely nicely. So as an aside, first we can define a mixture density as just the sum of the volume fraction times the density of the liquid plus the volume fraction of the gas times the density of the gas. So this here is called the mixture density. Okay, and
Professor?
yeah.
If all the pressures are the same, would the interfacial pressure also just be equal to P as well?
Yeah.
Okay.
But also I'm going to show later that the interfacial pressure, it doesn't matter what it is.
Okay.
Because what happens to this term right here?
The gradient of the volume fraction of the gas and the gradient of the volume fraction of the liquid.
Yep, I'm going to sum those two gradients, and we have two phases.
So it's going to equal to 1.
0.
Or 0, yeah.
Yep, so that's why I just left it general, is that it doesn't matter. Is that it basically drops out because this sum here is 0. Okay, so now using our definition of the mixture density, we can look at these time derivative terms and we can combine them because again, there's the same velocity multiplying them. So I can say this is the time derivative of alpha L rho L plus alpha G rho G times V. I just basically combine these two time derivatives and factored out the velocity. Well, lo and behold here, this here is just our mixture density. And so the sum of these two terms here just becomes basically just becomes the time derivative of rho m times our velocity. Okay, and so already we have greatly simplified here. We no longer have those nasty volume fractions here, so basically that's gone. We have now just a sort of a density of the mixture. Okay, now I got these two the two advective terms to deal with. Well, they work in a very similar fashion. Is you can combine these two terms here, and then when you combine them, you can factor out the common v squared terms here, and then you wind up with basically the divergence of v squared times this quantity here, which is defined as the mixture density. And so basically these two nasty terms here turn into a slightly less nasty term of the mixture density times v squared. Okay, and so you can sort of see now, if you were to add these two up, you're starting to get something that resembles very closely to your standard momentum equation. It's just that your density is a bit more complicated because it's a mixture of basically two different fluids. And you'll see that actually what we wind up with after everything is simplified is we end up with the usual normal momentum equation. Okay, So now we got these, we got these pressure, these are pressure gradient terms, not divergence. We got these pressure gradient terms here. Again, we can combine them. And this is gradient. And so we have the gradient of pressure times, then we can factor out the, we can factor out this common pressure between them. And we got alpha G and alpha L. And now the sum of the volume fractions has to be 1, as was stated earlier. And so basically this term here just goes to 1. And the sum of these two pressure gradient terms just becomes the gradient of pressure in the normal sense. Okay. And so now we got to work with some of the nasty interfacial terms here. And the note, I think I did this yesterday, but I'll do it again, is that this, by definition, the sum of the volume fractions has to be 1. So we can take the gradient of this, and the gradient of the sum of the volume fractions equals the gradient of 1, while the gradient of a constant is 0. And so then we can take, these are two linear operators, so we can move the gradient inside with basically no problem, which implies that the sum of the gradient of the volume fractions is equal to 0. Or if you expand this out for two phases, we have the gradient of alpha G plus the gradient of alpha L is equal to 0. And so that's where that relation that I used earlier sort of comes from. Just sort of comes from just playing with your vector calculus. Okay, so basically what this means is that the interfacial term with the gradient of alpha G and the gradient of alpha L, this term here goes away. And there are several other terms that are like that also disappear in the governing equations. Okay. And then also, what do we do with this term here? We had a velocity times the sort of mass, the sort of mass addition to the gas, plus the mass addition to the liquid. That should be liquid, not gas. Well, again, this here came from the control volume. When we did our control volume, I had this little slab here, and basically this came, this sort of phase change term was basically came from a mass exchange at the interface, which is right here, or if you have particles, interface is, and so basically m dot triple prime G is equal to negative m dot triple prime L, is that conservation of mass demands that. Okay, and so basically this term here goes away. And so what we are left with, if we use these simplifications on all of these terms here, and I have another sort of gradient, basically sum of the gradients of the volume fractions here. And if I basically work through all these assumptions, use the definition of the mixture density, what we wind up with is this expression right here, and it is nothing more than the normal usual momentum equation. Okay, and so it is more or less the same, except for you do need to be careful is that there is a mixture density, and so you need to be able to sort of compute that. That's usually very straightforward. And then also you need a model for the viscosity as a function of alpha T P and also the gradient of V. Okay, and so basically you need a way to mix to basically mix everything. And typically what's done is there's no good theory for this, so they just say that sigma will be equal, like one way to do it would be alpha G times mu G plus alpha L times times the viscosity of L, and that'd be the viscosity of the mixture. Okay, and that's just a modeling that's just a modeling approximation. There are as many ways of doing this as there are researchers developing these models. Okay, and so are there any questions with what I did to derive or to simplify this expression here? Okay, so I'm not going to do it for energy, but you can do the exact same thing. And if you do the exact same thing, you wind up with with an energy equation that is identical to the normal to the usual energy equation, with the exception that you have a mixture total energy, and this mixture total energy is just the sum of the total energies for all the different phases. Okay, but other than that, this is identical. The procedure for reducing the nasty conservation of energy equation for each phase is the same thing. You sum them all up, you apply the homogeneous flow, mechanical equilibrium, and thermal equilibrium. And if you do that properly, you will wind up with the normal, with basically with the usual moment, with the usual energy equation. And just like this for Q, you need to define a lambda for the mixture. And that's usually, I've seen this done usually the same way. Then also you need to be careful with the diffusion energy source. But I'm not going to get into those sort of really in the weeds type subtleties with this. I mean, yeah. Okay. Then, so using our assumption here is the final equation set, and I'm just assuming gas liquid, but this could be gas solid, or this easily extends to multiple to n phases, not just two. You can extend this very straightforwardly to say 10 different phases. Okay, and by phases, I'm using it in a very, or in this field in general, it's used in a very loose term, and so it just means 10 different things are, like anything that is not allowed to mix at the molecular level. Okay, and so our final equation set using with our 5 equation model is we have the volume fraction equation, which we're assuming is just a sort of passive scalar. We have conservation of mass for both the gas and the liquid. You still solve those independently. And the reason you solve them independently instead of combining them into one mixture mass equation is this allows you, is solving them independently, allows you to strictly conserve mass for each phase. And then if you conserve mass for each phase, then basically you also conserve total mass. Okay, and so that's basically why this is done. And this also directly gives you the alpha G rho G and the alpha G, or in the alpha L rho L, that is needed to define the mixture density. Okay, and then we got the normal when we got the sort of usual conservation of momentum and energy equations, and I just dropped I dropped the subscript M. It's just understood that in this sort of a multi-phase flow context, that if you see a quantity that does not have a subscript, it is a mixture quantity. Okay, and so are there any questions with this? And again, this is called the 5 equation model, because if I was to add them up, I get five equations if there are no species, or if it's non-reacting. Oh, okay.
Don't you have 3 equations for velocity? This is 1D flow, huh?
Yeah. It's 5 equations in 1D, and so that's where it gets its name. Okay. Then, if you have combustion, you have also species mass that you need to augment here. And so, and those are unchanged from what, from basically what I scribbled down earlier. Okay, and so, but if you solve these equations together with basically with a phase change model and a chemical reaction model, you have now a reacting flow for a multi-phase mixture. And to date, no one I know of, we're starting to do it now, has actually solved a reacting flow version of these equations for a fully compressible flow. It's sort of the numerical techniques for solving these efficiently and robustly and accurately have really just been developed here in the past 5 or 10 years. So, and so this is still very sort of cutting edge stuff here. But these equations have tremendous application for looking at spray combustion and like a scramjet, because you can assume fully compressible flows, shock droplet combustion, all sorts of really, really interesting, fun things. And hopefully our group can get some funding to examine some of that stuff. But we shall try. Okay, but now to complete the equation, or to complete the model, you need an equation of state for each phase. So gas and liquid is in that in principle you can choose any equation of state that you want for the gas, and another completely different equation of state for the liquid. And so you could choose whatever crazy shock compression equation of state that you have for a liquid. And then you can choose, I don't know, JWL products or BKW, or even ideal gas for the gas equation of state. And so you are free to choose any equation of state that you want for the gas and for the liquid. And then you need also a mixture rule for the transport properties. So I already sort of discussed this. But what's sort of common is, because there's no rigorous theory for these multi-phase and the flow mixtures, is that you just define a mixture viscosity as just the sum, as just the volume fraction weighted viscosities of basically each phase. You need a phase change model. So you need a sort of species production rate due to heterogeneous reactions, and you need m dot triple prime. Okay, and then of course, if you don't have phase change, then these are both equal to 0. And just make sure that for each phase, that the sum of omega dot heterogeneous for I in phase K equals m dot triple prime K. Basically, conservation of mass demands that. You need a reaction model. So for each phase, you need a complete reaction model. So for phase K, you would need to know how all the different components of that fluid react. And then also you need sort of diffusion and heat transfer models. So this would be the diffusion velocity, and also the heat transfer, the sort of heat transfer model too. Okay, so that is sort of Fourier's law, the sort of diffusion energy source. So all that stuff comes, all the stuff that I discussed basically came in earlier. Because in principle, you could have a real gas equation of state for the gas and a simplified equation of state for the liquid, and then all those evil thermodynamic derivatives, you're going to wind up needing them in this type of flow. And so that's sort of why we sort of went over that stuff, is to get into when you get into real gases and real multi-phase mixtures, and especially at the high pressure rockets and explosive type conditions, you wind up working with real gases. And so yeah, and so basically this sort of makes to me this that the fact that you've got this fairly general equation here that are very general. We have all these different terms that you need to model. To me, that sort of makes this like some folks don't like that. It's not fundamental enough to them because there's a lot of modeling choices. But to me, that's what makes it fun, is you really get to think about each and every problem, think about the model, think about the physics, and maybe set some of the stuff to 0 or find models. Basically that you can use. Okay, but these become very application specific. A model for droplet combustion in a detonation engine would be different than the model for if you're going to detonate an explosive underwater and you want to see how that bubble grows. Is that your modeling choices will be different for those two applications. Okay, now the question here is that for the chemical reactions and basically all that stuff, we're going to need to know what the pressure and temperature of the mixture is. But the equations the equations that we are solving, we have access to alpha times rho times v, and rho e. And so how do we find pressure and temperature from these variables here? Well, we apply our assumption of pressure temperature of pressure temperature equilibrium, and then basically find a common pressure and temperature such that our mixture density is satisfied. And so we know we can easily find the mixture density by basically summing up these quantities here, right? And so basically we know what that is, and we also know what the volume fraction is. So basically we can form the sum of basically alpha k rho k in basically two different ways. One is directly using data from our flow solver, and the other is using the volume fraction produced by the flow solver multiplied by our density that is assumed for our equation of state. So that would be the pressure and the pressure and the temperature. Okay, and so basically, this here provides one equation here. Is that we know what this is. We know and we know what the volume fractions are. We have our equation of state, so we know a functional form, but we don't know pressure and we don't know temperature. So that's one equation. Is that we can ensure that the mixture density is satisfied both from the governing equations and from the equation of state. So, but that only gives us one equation, and the other equation that we use is to ensure that the mixture energy, or that the mixture internal energy, and basically rho small e is just basically rho cap e minus the kinetic energy, is equal to the sum of the volume fraction, which we know, and in the equation of state for the density, and also the internal energy equation of state. And so both of these in general are functions of pressure, of basically pressure and temperature. And so here, what we have here is a system of two equations for two unknowns, pressure and temperature. Okay. Now, in general, this is a very evil, nasty, expensive Newton-Raphson method in our flows when we're dealing with like program burn, and we use this type of model to describe the explosive and the gas interface. If that model fails or it blows up, it is in this step right here. This is a very challenging step. So even though in principle, if you had 10 different phases with 10 completely different equations of state, in principle, you could solve these equations here for the common pressure and temperature, but the likelihood, but the challenge of just getting the solver to work to find that common pressure and temperature is extremely challenging, and it's very, and it's sort of not, it's sort of not ideal. And then also, you have some other sort of things to sort of worry about. Is, say your equation of state is for a solid. Solids admit with sort of solids, you admit negative pressure if it's in tension. And then if you have some gas, if you have a very small quantity of gas and it's next to a solid that is under tension, you may wind up with conditions where it is impossible for the gas, which only which can only have positive pressure, and the solid, which is at a negative pressure, it is impossible to get them to agree on a common pressure. And so there are little gotchas with that, and so there are a lot of subtleties to sort of solving these equations efficiently and robustly for a given application. Okay, so are there any questions? Are there any questions with this?
Yeah, I've got a quick question. So is this step right here, is this something that needs to be solved every iteration, or is this something that's done post-processing?
Oh no, this is done every single time you need pressure and temperature. which is basically every single time step at every single computational cell.
Yeah.
You have to solve this. So this
Oh.
is solved billions and billions upon billions of times.
So that's why the expensive Newton-Raphson method really puts a kink in the hose.
Yeah. Yeah, for our program burn model, if you ever noticed, in the very beginning, they sort of run kind of slow, and then they'll pick up in speed after all the explosive has burned out. That's why.
Okay. Yeah, that makes sense.
Is because all the interfaces of the explosive are gone, and so it's not doing this step anymore.
Hmm.
And so yeah, that's just part of. Yeah, that's sort of for these types of flows, even though in principle you can use more than two phases, you normally don't see more than two being done if the equations of state are basically arbitrary. There are some simple equations of state that you can apply these conditions to derive an analytical thing, and that would be only with very simple equations of state, such as what's called stiffened gas, which is just ideal gas plus an extra little pressure term. So you could say P minus P naught equals gamma minus 1 rho E, something along those lines. I can't remember the exact functional form, but with stiffened gas, essentially, there is a sort of pressure shift term, and there's also a shift for the internal energy, and then those allow you to actually approximate solids with a very simple equation of state. These are not used much for combustion because the temperatures of the gas and liquid using this model, or of the liquid, I should say, are completely hosed and completely wrong, because the specific heat is way off. Because you need to use a more realistic equation of state for a liquid or a solid if you care about the temperature. If you're doing an application like studying the shock wave interacting with a droplet, you sometimes don't care what the temperature is. And so you don't, and so using a very simple equation of state such as a stiffened gas is often okay too. Okay.
I have a question about the one of the assumptions we made. We made the assumption that all our phases are at the same velocity.
Mm-hmm.
Is that commonly used for solids and gases combined? Like, would you use this for aluminum particles being explosively dispersed?
Absolutely not.
Okay.
Yeah, not for that application. I'll get into those multi-phase sort of style models with particulate flows basically later. This here with this sort of model, the 5 equation model, what you're implicitly doing is that in each computational set, or basically you are assuming that you are resolving the interface between the gas and liquid, right?
Right.
So basically this type of flow, this type of model is appropriate for resolved So if you have a droplet, is that in the droplet, you're actually resolving it with, like on the computational grid. So if I'm to zoom in on the edge of the droplet, which I've poorly drawn right here, I would zoom in and the computational cell would look something like, it would physically look something like that, where I have the liquid right here. But then the computational cell it doesn't know that there is an actual curved interface there. It just knows that there is some alpha L in this computational cell, and there's some, and then there will be some gradient of alpha L. And then basically with this type of model, it's good for things that are like this. So if you have a spray atomization and combustion, this type of model would be really good for that. Shock droplet combustion, it's good for that. If you have an explosive underwater and you're detonating that and you want to see how the bubble grows, which is a very common test problem for these types of models, albeit not using realistic equations of state or explosive properties. But if you want to see how the bubble grows underwater and what happens to the water-air interface. This would be a very good model for doing things like that. But if you have, because in both of those cases, because you are resolving the interface, the assumption that the velocity of the air over here is the same as the velocity of the gas is normally pretty good. Okay, because again, you are resolving the interface. And if the velocity of the droplet is different than that of the gas, that will be just part of your, that will become the result of just part of your solution. Is that the average, that if you were to find the average velocity of the grid points containing the sort of droplet, they would have their own higher velocity. And because you are resolving the interface, all the boundary layer effects and things like that on the surface of the droplet would also be just part of the solution. Okay, does that make sense?
Yeah, that cleared that up a lot for me. Thanks.
Yep. But now if you have particles that are subgrid, well, they can be going all at their own different velocities. And now if you use Lagrangian particle methods, you can basically keep track of, in principle, you can keep track of the position and velocity and whatnot of every single particle. But for, say, explosive dispersal and combustion, where you have trillions and trillions of particles, that's not really sort of practical. And so a lot of folks, including myself, are using Eulerian methods. Again, they're based on the really generic equations that I derived earlier, but all this information of all the particles are basically averaged into basically into a volume fraction of the particles and a mean velocity of the particles at each computational cell. And the sort of air or gas surrounding the particles has its own volume fraction and its own velocity. And then you have a sort of drag model that is going to exchange momentum between the different phases. Okay.
Professor, I had a quick question about the grid. So would you use the same equation when solving that for both the boundary as well as the inside, or would you have like a condition where the inside is solved with a different equation?
No, here the inside and the outside are both solved using these same equations here. And so you sort of inside of the droplet, you still solve, say, this gas phase continuity equation right here. It seems wasteful, but it makes the code a lot fairly straightforward to implement. And so basically, you basically solve it as if there's gas and liquid everywhere, and then basically, if there are regions where there are no gas, then basically alpha G will basically just be zero as part of the solution. Does that make sense?
Yeah, that makes sense. So it takes care of it on its own.
Yep.
Okay.
Yeah, it is a bit wasteful in the sense that you have to, if you have, a giant region of air and a tiny little droplet inside of it, that you have to solve the liquid volume fraction equation everywhere, but that's just the way it is. The other alternative approach is to use these sort of level set methods. And those allow you to do whatever you want with the gas and the liquid, as long as you, with the caveat that that you can robustly couple the two together, which is not always the case. That's also a huge numerical challenge. Okay, but now just gonna finish up real quick. And so this volume of fluid or VOF method that I discussed, at least for compressible flows, they solve this 5 equation model with a special algorithm for basically alpha, for the volume fraction, where if I had this computational cell right here, and physically this is basically what the distribution of the volume fraction of the gas in liquid would physically be. What the volume of fluid method attempts to do is it attempts to sort of reconstruct this exactly. And so what it will try to do is basically the code does not know that there's supposed to be a little quarter circle of liquid in here. But what the VOF method will do is it will look at the volume fraction of that grid point and the volume fraction of all the neighboring grid points, And basically, it will attempt to reconstruct the sort of volume fraction in the computational cell so that it would approximate it something like this. And then basically, and then basically what that does then, that allows you to more precisely define the interfacial, the volume fraction at the cell edges, and sort of things like that. So you can actually basically move around the sort of different phases far more accurately. And then also the algorithm is defined to keep the interface sharp. Is that the interface using a volume of fluid method is defined, basically the volume of fluid method works such that the entirety of the interface is contained within one cell. And so the cells that contain both the gas and liquid are by definition, if the volume of fraction method is working properly and you've coded it upright, it is spread over exactly one computational cell. That's just by definition of how it works. And so it has very sharp interfaces, and there are very special algorithms for basically dealing with that. And so I'm not going to get into those. They're fairly complex to implement. And the sort of complexity is actually reconstructing the interface, the subcell interface, based on the surrounding volume fractions. That is the expensive step, because there's all sorts of conditions that you've got to sort of look at and see, and then also account for triple points if you have 3 phases. So it gets to be kind of a mess, but it is very accurate if you can get it to work. Okay.
From that standpoint, is this capable of breaking the droplet into 2?
Yep.
It still is. Because it seems like it wants to merge like components next to like phase, or like phases next to like phases. So I would imagine if it's splitting, it would violate that.
No, it actually, that's all done in the, I mean, I've given a very hand-wavy description of the reconstruction algorithm, but they got ways of determining whether there's a droplet breaking up and sort of things like that. And in fact, for the volume of fluid methods, spray atomization is the traditional application for it. Okay, then there are diffuse interface methods. Again, these solve the 5-equation model, but they just solve them normally. And so the interface will be smeared over many, many computational cells. So if you have a droplet, is that the surface of the droplet will not be sharp, but it'll be smeared over, say, 5 or 10 computational cells. Okay, and so for some applications, that's okay. For some, you want it to be sharp. And then there is, I'm not going to get into them, and we are starting to use them quite a bit. It's called Think. And basically, it is a compromise between VOF and the diffuse interface methods. Is that basically it avoids the complexity of the volume of fluid, and you solve it using a diffuse interface style method, but it's a special technique that is defined to basically spread the interface over a small number of computational cells, say 2 or 3. And so that avoids but it doesn't have the inherent complexity of volume of fluid methods. And this is what basically we are starting to use for these types of flows. And so and they work very well, and they're not as sharp as VOF, but they're mass conservative, and for like gas liquid flows, they work very well. And so, but anyways, and so again, but if you hear the phrase VOF or diffuse interface or Think, typically they are all solving the 5-equation model, and they're just different solution techniques for them. Okay, are there any questions? Okay.